Aman, is my screen visible?
Yes, sir, definitely.
Okay, okay. So this first the topic is modeling and analysis of bridges. So although our title is dynamic modeling and analysis, but here we will be considering the modeling in general and specific aspects related to dynamic analysis. So dynamic behavior of the bridges, when we talk, there are three types of actions where the dynamic behavior can occur. One is under the moving load itself. So when a vehicle or train is moving over the bridge, it is causing an impulsive load on the structure because it is varying with time. So impulsive type of load we get, and under that impulsive type of load, the bridge is set to vibrate. And due to those vibrations of the bridge, the dynamic response is more than the static response, and we commonly know as the either impact factor or CDA, coefficient of dynamic augmentation. So both are taking care of this dynamic effect. The problem occurs when there is a resonance between the structure and the moving load. So moving load is also causing a periodic force which is having some frequency, and then if that frequency matches with the frequency of the structure, then we have a resonance like situation, and there the response of the bridge increases abnormally. So in our normal analysis, we have to avoid that condition. So that is one aspect which we are going to cover in this course. The second action under which dynamic behavior of bridges is important, perhaps all of you are aware, that is earthquake. So when earthquake is causing shaking of the ground below our structure, the structure, whether it is building or bridge, is set to vibration, and due to those vibrations it will have a dynamic behavior. In case of earthquake, there is additional complexity in the behavior of the structure because we design our structures to yield during earthquake. We never design our structures to remain elastic during earthquake. So our structure is subjected to non-linear dynamic behavior, which makes that behavior a little more complex. But in our conventional design, we don't really perform nonlinear dynamic analysis. We perform linear dynamic analysis only, and the effect of nonlinearity we take into account indirectly through response reduction factor. So that is the second type of action which we are going to cover. There is also a third action which can set vibrations to our bridges, especially when the bridges are flexible, like the cable stayed bridges, or the bridges are very tall, so which are flexible. So that is due to wind. So wind can also induce aerodynamic effects, and the structure is set to vibration. And there also, if the frequency of the structure somehow matches with the frequency of the vibrations caused by the wind, then the effect can be devastating. So failures in the past have been reported in especially in case of cable stayed or suspended suspension bridges, where the wind can cause excessive dynamic response. In this course, we will not talk about this third aspect. We will limit our discussion about the first two aspects only, and in future sometime we will talk about the third aspect as well. So we will start with first the modeling of the bridges, and this modeling is applicable to all types of analysis. So before taking up the modeling, let us see what are the important aspects of the behavior of bridges which we should cater in our model. Our model cannot be a realistic model if it is not able to represent the behavior which is particularly important in case of earthquake. So let us see what type of failures and damages have been seen in the past earthquakes. Very quickly, I will go through this. So this first one shows the damage to the bearing, or rather connection of the bearing to the structure. So this is one of the ignored parts. It is not given due attention in neither in modeling nor in design. So whatever modeling we are doing, we should model in such a way that the forces which we are expecting in the bearings and what we have to use for design of bearings and connection of the bearings with the structures, the model should be able to represent that realistically. Then the second type of failure is the shear failure of the piers. So different types of failures have been observed in piers. And shear failure is the most common, and it is also brittle failure. So when shear failure occurs, adequate energy dissipation does not is not available, and due to that there is a sudden failure. Then and bridges are different than the buildings because bridges are like inverted pendulum, and that behavior of the bridges we have to take into account. Most of the bridges are statically determinate, and because of statically determinate, if the damage occurs at one location, if the hinges are formed at the base, then it will topple like an inverted pendulum because it is not having any second line of defense. It is having no indeterminacy. So this type of failure has been observed in the past earthquakes. And here the curtailment is also important. And what was observed during Kobe earthquake, that the inadequate curtailment was responsible. So behavior of the pier should be adequately represented. Many a times we are representing the piers by single frame element. But in case of tall piers, that single element may not be adequate. So we may have to use multiple elements for piers, modeling of piers. But what we understand is that the piers are the most important component of the earthquake which undergoes damage. So pier modeling in a bridge is most critical. We should give adequate attention to modeling of piers. Different types of piers. Here, the pier failed due to flaring of the column of the pier near the joint with the bridge. So when the pier is having this type of behavior, it is important to model that. So based on this understanding of the behavior, let us see how we can analyze the buildings, and accordingly we can model the buildings for earthquake and also for moving load. So different components of bridges which we have to model. First of all, the superstructure. So whatever slides I have shown you, you have seen that in most of the cases, superstructure was not affected, except that the connection of the bearing with the superstructure that got damaged. So in most of the cases, the superstructure during earthquake is acting like a mass, but it is also subjected to bending, especially if it is flexible. And under moving load, the superstructure is the most important component. So the response under moving load will be different. There, it will be the superstructure mainly, which will be getting deformed, and we need to model the superstructure. So superstructure, it is subjected to mainly bending action. So it can be modeled using frame elements, and we can model either using single frame element or we can use a grillage of frame elements. So we will discuss that in more detail. Then we can also use continuum finite elements like the shell elements. In case of truss bridges, we have to use truss elements. And in case of cable stayed bridges, we have to use cable elements. So superstructure can be modeled in different ways, depending on which aspect of the behavior of the superstructure we are interested in. Then the second important component, which we also saw in the damage photograph. So these are the bearings. So bearings are usually modeled just as restraints. So restraints are the boundary conditions. So bearings, if suppose I'm having a superstructure supported on a rigid abutment. So sometimes we just consider the abutment as the rigid support, and whatever restraints are provided through the bearings, those restraints we will assign to the superstructure. For example, in case of a pinned bearing, it will be restrained against translation in all the three directions, and rotations will be allowed. Then we can also model bearings as constraints. So when we are modeling the pier and we are modeling the superstructure also, then between the superstructure and the pier, we have to provide certain constraints which represents the behavior of the bearings. When the bearings are deforming, we can use elastic elements also. And when the bearings are expected to deform inelastically, then we can use inelastic link elements also. So in case of base isolation bearings, the bearings are expected to deform inelastically. So if, for example, if it is a friction-based bearing, then when the friction is exceeded, sliding is started, the behavior becomes nonlinear. So that inelastic link we have to use. Then in some bridges, In parallel to bearings, we provide dampers and shock transmitting units, STUs. So the purpose of these dampers is to dissipate the energy during earthquake. And the purpose of STUs is to allow the displacement of the superstructure with respect to the pier cap in normal loading, that is temperature and gravity loading. So those there the deformation occurs slowly. So under slow movement, these are not effective. But for example, like in case of earthquake, there is a sudden displacement of the superstructure. Then these are locking the superstructure with the pier cap, sorry. So STUs are nothing but these are also very high damping dampers. And because of the high damping, these can allow the slow motion, but these cannot allow velocity. If there is a high velocity, then these will provide large force and it will actually act as a lock. So these can be modeled using dashboards, nonlinear link elements, and then sometimes these STUs, these will allow certain displacement, and after that these will become effective. So that can be modeled using gap and hook elements. So in any software will provide these elements are available in the libraries of those software. So next important component are piers. So we have seen that the piers are subjected to most of the damage in case of the bridges, because in case of bridge, these are the piers which are dissipating the energy, not the beams. Like in case of building, the energy dissipation will depend on the beam. But in case of bridges, the beams are either not there, or even if those are there, like in the superstructure, those are connected through bearings, and those are not subjected to any yielding during earthquake. So piers are subjected to yielding, and that's why these piers needs to be modeled properly. So generally we use frame elements, but in case of wall type piers, we can use even shell elements. So sometimes we also use shell elements. So one of the damage photographs where I have shown, there was shear failure, and the shear failure was because the dimension of the pier in that direction was larger, and it was acting like a short column in that direction, and due to that the failure in shear occurred. So if that type of situation is there, we have to model the pier using shell elements. Then foundation on which the bridge is resting, it is important. So we model the foundations either as grillage. So if, for example, if it is an open foundation, we can model it using a grillage or using shell elements also. Similarly, if it is pile cap, we are using a pile group as the foundation. So piles we can model as frame elements, and pile cap we can model as shell elements. Then the soil surrounding the foundation, that is also part, or that is also affecting the behavior of our structure. That is also providing some flexibility for our bridge to move. So in some cases we need to model soil also, but in most of the cases the deformation which is caused due to soil is much less in comparison to the deformation caused due to the other components of the bridge. So in that case, we can ignore the effect of soil and we simply fix at the base of the pier, and just at the top of the foundation, we fix our structure. But if we want to have a more realistic analysis and we are not sure about how much the soil is contributing, we can model soil also along with the structure. And soil can be modeled either using a solid continuum, so 3D solid elements or so-called brick elements we can use. If we are making a 2D model, then soil can also be considered as a 2D continuum plane strain. So these are the commonly used elements. And then soil can also be modeled as a series of linear springs and dampers. So dampers are representing, because soil, when it is deforming, it is also dissipating energy. So that energy dissipation we need to take into account by applying these dampers. So we can have a combination of linear springs, and behavior of soil is highly nonlinear. So many cases we are modeling the soil using nonlinear springs plus dampers. And then abutments. So abutments are provided at the end of the bridge. So these are supporting the bridge at the ends, and these can be sometimes modeled in our bridge model just as supports. So boundary conditions, which I explained earlier also. So these can be assumed to be rigid, and whatever the bearings, whatever type of the bearings are provided at the top of these abutments, accordingly we can provide the boundary conditions or the support conditions. Then abutments, if we want to take into account the flexibility of the abutment into account, or we want to design uh, abutments also, in our model we want to consider that, then we can model those as grillage or shell elements. And along with that, we have to model the soil also, either as continuum or as springs. Then we will get the true behavior of the flexibility due to abutment. So here what we will do, the course we have planned, we have developed in such a way that it is aimed to practicing engineers. Initially we thought, but now I see that a number of students have also joined. So what we understand is that our participants are somewhat familiar with the modeling and analysis of the bridges, and they have some idea of the vibration characteristics of the bridges, theory of vibration. So we will be, they have some experience on the software also. So we will not be going into the theory of vibration or what we call structural dynamics. We assume that you have that background. So if there is any question related to that, please do write in the chat box. We will try to answer, but I'm not going to cover the theory of vibration step by step here. We will rather focus more on what type of elements we should use, how we should create a model in a software so that it is realistically representing the behavior of the bridge, and how we can interpret the results. So our focus will be more on these aspects. Okay, so when we are doing the modeling of the bridges, different uh, types of models, depending on how much sophistication we want, different types of models are available. The simplest model is what we call single pier model. So we model individual piers. So pier is modeled as a vertical frame element, or it may be modeled as a series of vertical frame elements. So a single frame element is shown in this case, and the mass of the superstructure is lumped at the top of this vertical frame element. So how the mass is lumped? It consists of the mass of the pier cap plus some portion of the pier, roughly 50% of the pier also, pier mass also we can lump here. Then it is also consisting of the mass of the superstructure. So how the mass of the superstructure will be contributed to a pier will also depend upon the bearing arrangement. So if we have a normal simple supported bridge in which one end is having fixed bearings, other end is having roller bearings. So in the longitudinal direction, the whole mass of that bridge will be lumped to the pier to which it is connected in a rigid manner. And the other pier will be relieved of that mass. In transverse direction, in any case, the two piers which are supporting the superstructure will be sharing the mass or the inertia force from the superstructure. So 50% mass will be supported or lumped on each pier at each end. Then we have to also understand that the point of action of this mass along the height is different. So for example, here the point 1 is shown. This is showing the center of the pier cap. So the pier cap mass will be lumped here. But if we are lumping the superstructure mass to this, then the point of action of the superstructure mass in in longitudinal and transverse direction will be different. In longitudinal direction, the mass of the superstructure will be effective at the center of the bearing. So it should be lumped at the level of the bearing somewhere here. So here the superstructure mass will be lumped. The live load in longitudinal direction we don't consider live load, but in the transverse direction we consider the contribution of live load also. So live load will be acting certain height above the bearing also. So the live load will be acting somewhere here. So not only we have to consider the proper element for modeling the pier, we have to also model the mass separately or appropriately. So we have to understand that this single pier model, this is a simplest model, and that's why it has its own errors. It is giving us an approximate analysis, and the mass cannot be lumped at one point. It will be lumped at the corresponding CG of that mass. Then in many cases the pier may be flared. So if the pier is flared like this, then modeling it just by one element will not be sufficient, and we have to model it by a number of elements along the height, and the sizes of these elements may vary, and the size of each element we can assign as the average size within that height. Now when our pier is tall, even if it may be prismatic, its size is not changing, but if it is tall, then higher modes in which the pier is also vibrating in different modes, those modes we have to consider by dividing the pier into number of frame elements. So in case of short prismatic piers, we can use single frame element as shown in the center figure, and in case of either a tall pier or when the pier is changing in cross section, we have to use multiple frame elements. So this is what our single pier model is, the simplest model. And here the modeling of the soil is also shown through springs. So soil can be modeled using appropriate springs. Then when we are modeling the soil surrounding the foundations, so in some cases when the foundation deformation is large or significant, there it becomes important that we model the foundation also. So foundation, as I said, can be either modeled using continuum or it can be modeled using springs. So for example, here what is shown is a single monopile structure with pier connected to the monopile. So here this monopile or the single pile is uh, connected to a series of these springs. So these springs are presenting the soil, and these springs can be linear as well as non-linear. And sometimes, in addition to these springs, we also provide dashboards, dampers, which are representing the additional damping which is caused due to deformation in the soil surrounding the foundations. And when we are modeling like this, you can understand that the bending moment and shear force diagram below the foundation level is going to change. Now, what effect it can have to the structure above the foundation level? So, soil will be providing some additional flexibility. Due to that, the period is going to change, but the change in the period will be negligible, generally very small. So, there is not much effect on the forces. But because of the deformation in the foundation, there can be additional rigid body rotation, and due to that rigid body rotation, we can get additional P delta effects. So modeling of the foundation can be important when the deformations in the foundation soil are significant, and it can give rise to additional P delta effects. So when the ground also deforms, the soil also deforms, we will have one is the translation. So this translation will not have much effect on the behavior of the superstructure, but the rotation of the foundation, that is important because that will give rise to additional displacement, and due to that additional displacement, there will be additional period effects. Now, in case of modeling of the bridges, the modeling of the superstructure is also crucial, and superstructure can be modeled in three ways. The simplest model of the superstructure is a spine. So in this case, we can see that the substructure is also modeled with frame elements, and the superstructure is modeled by one line of frame elements. So we can see that these frame elements, there can be a single element running between two piers, or there can be multiple elements. Sometimes we assign multiple elements, especially when we are doing a moving load analysis. Then we have to mesh this span into a number of linear elements, and these linear elements are connected to the frame model of the pier through appropriate constraints here. So those constraints That is the relationship between the degrees of freedom of the superstructure and the degrees of freedom of the substructure. So those constraints are appropriately assigned as per the bearing arrangement. So this is the simplest model, and we can have a more improved model in which the superstructure is not represented by single beam but a grid of the beams, which we call grillage. So the beams are running in longitudinal direction as well as in the transverse direction. So this model will be shown today in the afternoon session in more detail, where a bridge will be modeled using this grillage. And here, because we are having the members running in both the directions, and these members are representing, the transverse members are representing the slab. So we have to avoid that the mass of any component should not be considered twice. So some of these elements we have to assign with zero density if we are considering self-load command. Then we can also model any superstructure, any shape of the superstructure using finite element. So we can have continuum finite element, and the shell element are the most commonly used elements to model the bridges. In some cases where we are interested, let us say there is a pre-stress bridge and we are interested in local distribution of the stresses. In that case, we may even require solid element modeling, but generally we don't use solid element modeling because that will result in very large number of degrees of freedom. Very large number of elements and nodes are required, and that will make the problem very, very heavy. So when we are generally doing the earthquake analysis, this D spine type of model is most commonly used. When we are running moving load analysis, then this grillage analysis will be more useful. So we will see that how it is done in the numerical examples, hands-on examples in the evening. Now another issue is in case of skew and curved bridges. So when we have skew and curved bridges, the superstructure not only translates in longitudinal and transverse direction, it also rotates. Now that rotation cannot be modeled using a single pier model. So we have to use a 3D model, as I have explained, as I have shown in the previous slide. So we have to consider that 3D modeling we have to do, and where the superstructure can be either modeled by a single element or a grillage or the finite element. But we have to consider the spatial variation or spatial arrangement of the piers and the superstructure, so that when it is subjected to earthquake motion, its torsional motion, that is the rotation about the vertical axis, that is also simulated during earthquake analysis. Then when we have the bridges with unequal pier heights, where the pier height, for example, in the hilly regions, the pier height may be changing. So when the pier height is changing, some of these piers are more flexible as compared to others. And when these are more flexible, the superstructure will also undergo rotation. And due to that, the mass participation at a particular pier will also change, because the mode shape will not be in the form of translation alone. The mode shape will have rotation. And when we are considering the mode shape in the translation of all the piers is not same. The translation of the piers will be different. And when the transverse displacement is different at different piers, the mass participation at that pier will also change. So it can sometimes cause very significant effect. So in such situation also, we have to consider the 3D model, and we have to perform at least mode superposition analysis. If we are not doing even if we are not doing a time history analysis, at least the mode superposition analysis using response spectrum has to be used. Now this is a typical example of a composite girder modeled using grillage. So grillage, as I told, is made of beam elements, frame elements. So these are line elements. So actual model will look something like this, but when I render it, when we consider the three-dimensional extrusion of these members, then it will look like this. So actual model is like this, but the superstructure is modeled with a grillage. So you can see this is modeled with a grillage. The pier is modeled using frame elements, and the pier cap is also modeled using frame elements. And what we have between the grillage and this frame element, there are peerings, which are not being seen here, which are being modeled using link elements. So in the evening, when Mohit will be demonstrating you the same example, there he will show the more details how we can assign the peerings. So in 3D view, it may look like the bridge, but in actual grillage model, when we are representing the superstructure and substructure by line elements, then it may look very differently. And you can see here that the longitudinal members are running along the girders because those are our main stiffness elements. We can have additional longitudinal members also for the purpose of transfer of load as well as for simulating the stiffness. And in the transverse direction, we are having these fictitious beams. Actually, there are no beams in the transverse direction. So all these beams are fictitious. So these are representing the slab behavior in the transverse direction. So you can see that the slab is considered in the longitudinal direction also when we are modeling these girders and these other longitudinal elements. And the same slab is being modeled in the transverse direction also by these transverse beams. So the slab is being considered twice. So as far as this bending is concerned in the two directions, that is fine, but we should ensure that the mass should not be considered twice. So that's why generally these transverse beams which we are providing here, these are provided as massless so that the self-weight is not considered twice. Then this is a truss. In case of truss, I mean, this is the simplest structure and we can model using truss elements, but we have to take care of the connections between different elements. So two types of connections may be there in case of truss bridges. One is the simple connection. So in simple connections, we are connecting two members through their webs only. So if I'm connecting only the webs, the shear transfer and axial load transfer can take place at that joint, but the bending moment transfer cannot take place. But if I connect the flanges also, so in many cases, the top and bottom cord is connected along the web as well as spliced along the flanges also. If that type of connection is done, then this becomes a moment connection. And in that case, we should model the top cord and bottom cord using frame elements, not using truss element, but the frame elements, where the moments can also be transferred. So moment can be transferred from one bottom cord element to the other bottom cord element. But the other connections, the vertical and the inclined members, there it is possible that only the webs are connected. So those will not be able to transfer any moment. So these we can transfer using truss element. Sorry, we can model these using truss element. So which element we have to use will depend upon the joint condition. So we should look at the joints or whatever type of the joints we are proposing. Based on that, it will be decided whether the moment degree of freedom will be there or it will not be there, and whether it will be connected rigidly or integrally with moment connection with the adjacent element. When we render this 3D view, we see it like this. And this is a typical railway bridge. And what you see here, these are stringers. And these stringers are just below the railway track. And the load from the railway track is first being transferred to these stringers. So these stringers are acting like beams. And these stringers are transferring the load to the cross girders. So to the truss element, actually the load is being transferred at the nodes only, as is the condition in behavior of trusses. And the bending is taken care of by these stringers. So these stringers are modeled as beams, and because our train will move on these stringers, so the stringers has been also fine meshed. So you can see that the mesh is quite fine. Small elements, beam elements have been used here, so that the wheel movement when it is taking place on the stringer can be captured correctly. The load can be transferred through these adjacent nodes. Other elements you can see, even if we are modeling the bottom element as a beam element, when the joints are moment joints, the moment can be transferred. We can model it by a single element, and all the truss elements can be modeled by the single element. If we refine the meshing here, if we put more finer meshing here, we are not going to get any advantage. And there is no disadvantage in terms of the accuracy of the results, but in terms of the computational time, larger the number of elements, more time it will take to run. Now, in case of continuous bridges and integral bridges, we can model the series of the piers and the boundary conditions. If it is integral, it will be monolithically connected with the superstructure. If it is having bearings, then it is a continuous bridge on bearings. Then the bearings will also be modeled. Let us say this is the superstructure, the cross section of the superstructure. Interestingly, this cross section also we can represent by a single beam. In many models, although this cross section you can see it is quite complex, but we can model it by a single beam along the centroid of this. So we will assign a longitudinal beam at the centroid of this cross section, and the properties A and I will be assigned based on the cross-sectional area and the moment of inertia of this. Similarly, the pier can also have a number of types of cross-section. It can be even a hollow pier. So whatever properties of this cross-section are there, we will assign to these piers. And it will look something like this. So I have shown here the extruded view. Here the superstructure is modeled by a single beam element. And why you see these transverse lines? These are because I'm showing you the extruded view, but actually this is just a line which I have not shown here. Similarly, these piers are also just lines. So what you see these different elements, actually the pier has been divided into a number of frame elements. That's why you see these lines. So don't think that I have used shell element or any other element here. It is simply a spine model, single spine model, where the spine is modeled by a frame element, and that frame element is finely meshed so that we can take into consideration the distribution of the load when it is moving over the bridge. Then in case of cable stayed bridges, along with these elements which we can use to model the superstructure and the piers or the pylons, we have cables. So these cables have a very special behavior. So these cables are different than frame elements and even the bar or truss elements. So how these are different from the frame elements? The frame element has bending stiffness. So when you have a beam and subject it to lateral load, it will bend, and in that process it will provide certain resistance to transverse force. But the cables have no resistance in bending. Those are flexible in bending. So these cannot provide any lateral resistance, and these cannot also provide axial, or these cannot resist axial compression because these are flexible. So being flexible, these can resist only tension, and when this cable will be expanding in horizontal or inclined direction from one point to the other point due to gravity action, gravity is acting perpendicular or at an angle to the cable. In that case, there will be a sag in these cables. So we have to take into account that sag also, and due to the sag, it does not remain straight. And when we are applying the force, axial force to this cable, first the sag, or what we call catenary action. So that due to that catenary action, first the force will be consumed in straightening this cable. So it will be subjected to tensile stresses, and at the same time it will become straightened up. So the displacement in the longitudinal direction will be contributed not only by axial deformation of the cable, but also by change in its shape. And that's why its behavior is nonlinear, or what we call geometrically nonlinear behavior. So this geometric nonlinearity of the cables also we have to take into account. How we practically model the cables? The most commonly used model is truss element in case of cable. And sometimes it is necessary that we use truss element. Now, when I said that it cannot take compression, still we are using truss element to model it, because the construction of these bridges is usually in segments. So there is a sequential construction. And when we have to take into account that sequential construction and we are superimposing the loads, it may be necessary that we consider different forces which are added in each segment. Suppose I am using an element which cannot take compression, which is representing the cable correctly. So what will happen? In some stage, the additional force may be tensile, and we can't superimpose that. So for the purpose of this stage analysis and superposition of the forces, we model the preliminary analysis we always do using truss element, which can take compression as well as tension. Although real cables cannot take compression. Then if I want to model the real behavior, then I should have an element which should take only tension. It should not take compression. Now, this type of element can be either available in the library of the software, or we can use a hook element. So when we are using a hook element, then this hook element can take tension, but in compression it will lose. It will become looser, and it cannot take any compression. So we can use a combination of a hook element and a truss element to model tension only truss element. But this hook element will work only in nonlinear analysis. So this will require, if we want to do an analysis where tension only element is to be used, we have to perform a nonlinear analysis so that every step it checks whether it is subjected to compression and tension, and accordingly it provides the stiffness. Then we have a nonlinear cable or catenary element. This is the most accurate element, which takes into account both the effect. It takes into account the tension only behavior. At the same time, it also takes into account the catenary behavior of the cable, and it is a nonlinear element. It will require a nonlinear analysis because the shape of the catenary will change at every step of the loading. As the loading is changing, the force is changing in the cable, its catenary shape is also is changing, and this takes into account the geometric nonlinear behavior of the cables. Now it has been observed that this geometric nonlinear behavior of the cable is actually significant only in case of long cables. Generally, if the cable length is more than 150 meters, then the catenary action will be very significant. In case of smaller cables, for example, if we have extra dose bridge where the length of the cable is not that large, so in that case, we can ignore this catenary effect, or we can take this catenary effect into account approximately using an equivalent stiffness. So in case of this equivalent stiffness, the catenary effect is compensated by changing the modulus of elasticity. So expressions are available in literature using which we can calculate the equivalent modulus of elasticity of the material, the steel, which can take into account the catenary. Now, in case of modeling of cable stayed bridge, two possibilities are there. In one case, the single plane of cables is there, and the one which I showed you earlier, there are two planes of the cables. So you can see that the superstructure here is modeled using a grillage, where we are having longitudinal members as well as the transverse members. Here only two longitudinal members corresponding to the girders are shown. That is also adequate, but sometimes we may need multiple elements. Whereas here, when we are having a single plane of cables, the cables are vertically arranged in a single plane. In that case, we can even consider single spine model. So the superstructure in this case has been modeled by a single frame element. And what you see in 3D is actually the extruded view of that line element. Now coming to the analysis. Once we are done with the modeling, we have to choose appropriate analysis, and different sophistications in the analysis are also possible. So in case of earthquake, in tomorrow's talk, I will talk about the different types of analysis which we can do under moving load. Here we will talk about the different types of analysis which we do for earthquake. So for that, understanding that analysis, we need some background of theory of vibration. So any structure, whether it is a bridge or a building, it vibrates in different modes. So there are what we call natural modes of vibration. So a structure consists of a number of such modes, and the total number of such modes is equal to the number of degrees of freedom in our structure. The mode shapes, each mode is having a corresponding mode shape. So what mode shape I have shown here are actually for a building. So for a typical vertical cantilever, that is a building, or if we have a bridge, where we are considering just a single pier. So it will have modes like this. If we have made a 3D model of our bridge, then these mode shapes will be in the horizontal plane. So in the horizontal plane, we will be having different shapes. But each mode has its characteristic shape, deformed shape, which we call mode shape. And the shape is also important. From the shape of that mode itself, we can identify that which number of mode it is. And the response of the actual structure is response in all these modes. So the response in these different modes is superimposed during earthquake, and then we get the response of the structure. So one very convenient and computationally efficient method is that where we analyze the structure as a number of single degree freedom systems in different modes. So that is a very common model. So rather than analyzing the structure as a whole, we will consider the structure as a superposition of the response under different single degree freedom systems, and the period of this single degree freedom system is corresponding to that mode. So corresponding to each mode, we have a single degree freedom system, and this single degree freedom system has the period of vibration of that same mode. So we can see here actually these uh, modes are arranged in order of increasing frequency. So in order of decreasing frequency, the highest frequency, the lowest frequency we assign the first mode. So the first mode correspond to the lowest frequency, and as the mode increases, the frequency increases. So these are arranged in the order of increasing frequency. The fundamental mode has the lowest frequency and has the longest period. And that's why I have represented it by the tallest single degree freedom system, which will have the longest period. It will vibrate slowly. And as the number of modes goes on increasing, the period goes on reducing, or the frequency goes on increasing. So not only frequency is increasing, the contribution of these modes also goes on reducing. And that gives us further benefit that we need not to consider all the modes, because the maximum contribution is coming from the first mode itself. And as we consider higher and higher modes, the period is reducing, and at the same time its contribution is also reducing. So generally, if we consider initial 3 to 5 modes, we get enough accurate results. And the code provides for buildings as well as bridges that we should consider as many modes as are giving 90% mass participation, because each mode has some participation in the response of this structure, and that contribution in the response of the structure can be quantified in terms of modal mass participation in each mode. So we can calculate how much modal mass participation of that mode is, and we have to consider as many modes which are providing 90% mass participation, but it can simplify our calculation drastically. We have, rather than analyzing n degree of freedom system, we are analyzing few single degree freedom systems, and that gives us quite accurate results. So this concept is very commonly used in all our analysis. And another advantage we will discuss in the afternoon talk, that the response of a single degree freedom system for a ground motion can be read directly from the response spectrum. So the most simple analysis is in which we consider only single mode of vibration. So I told you that the contribution of the single mode is maximum, and it goes on reducing for the higher modes. So suppose my single mode itself is contributing more than 75% mass. So in that case, it may be accurate to consider the first mode alone. And in that case, what we do, the response of the first mode can also be read directly from the response spectrum. So most of the time, design response spectrum is available to us. So we can read that directly, the response of the single degree freedom system directly. And actually, we read spectral acceleration SA, that multiplied by the mass of the structure will give us the force in this single degree of freedom system or the structure. And this method we call equivalent static analysis. Although it is not entirely static, because we are taking into account the period of vibration. So dynamic characteristics of this bridge, or if it was a building, we are taking into account through the period, but we are considering only one mode. So that is the limitation of this method. So we can overcome that by considering number of modes. So we consider several modes. If we consider all the modes, the analysis of our structure will be same as we will obtain by direct time history analysis of our structure by considering all the degrees of freedom. So this analysis, the same response we can get if we consider all the modes and subject the single degree freedom system corresponding to each mode to the same ground motion. So the same ground motion is applied at the base of all single degree freedom system, and the response of these single degree freedom system can be quickly obtained because analysis of a single degree freedom system even to time history is much faster than the analysis of the direct full structure with all the degrees of freedom. And then we can simply add the response of these single degree freedom system multiplied by the corresponding mode shift. So we have to keep in mind that the single degree of freedom system is going to give us response only at one point. But in the real building, we are expecting the response along all the degrees of freedom. So how I will get the response of different degrees of freedom corresponding to this mode? I have to multiply this response with the corresponding mode shift. So when I take that corresponding mode shift into account, then I will get the response at all degrees of freedom corresponding to each mode. And then I can add that response in different modes to get the response of the structure. Now, this can also be expedited by reading the response of the single degree freedom system corresponding to different modes using response spectrum. So when I'm using response spectrum, I can get the response of the structure by taking the response of different single degree freedom systems. But we have to keep in mind one thing, that here when we have done time history analysis of the single degree freedom system, the peak response of these single degree freedom systems were occurring at different time instants. And response spectrum is giving us peak response only. It doesn't give the full response with time. It gives us only the peak response. Peak response corresponding to this period, I can read from directly. So I'm getting peak response, but those peak responses are not occurring simultaneously. Those are occurring at different instants of time. So it is not reasonable, it will be too conservative if I'm adding those peak responses, peak response of each single degree of freedom system directly. So that absolute sum is not realistic. So to make the response realistic, we have to combine the peak responses appropriately, and two methods of that combination are there, SRSS and CQC. The details of these methods are available in any theory of vibrational structural dynamics book, and the option is available in all the software. So we can use either SRSS or CQC. Most of the times we should use CQC because this can take care of all the situations, but SRSS is applicable only in certain special conditions where the modes, different modes, or the period of different modes is well separated. So if the periods are close, then SRSS may not give us the correct result. So CQC is a better method, more realistic method of combination. So we should use most of the times CQC. Then we can perform the analysis, as I said, under time history as well as response spectrum in different modes and combine. But here again, I am considering only few modes. I'm not considering, generally we are not considering all the modes. And it may also be possible in many cases that you cannot excite all the modes. The frequency of some of the modes may be so high that you are not able to excite. So in many cases, it may not be possible to achieve 90% mass participation. So what we should do in that case? In that case, this mode superposition method, neither using response spectrum nor using time history is valid. In that case, we have to go for direct time history analysis of our structure. So we will make a multi-degree freedom model of our superstructure, taking into account the superstructure as well as the pier, and masses will be lumped at certain nodes. So at those nodes, we will lump the mass. and we will perform the time history analysis of this multi-degree freedom system together. That is why we call it direct time history analysis. So we will perform a direct time history analysis of the multi-degree freedom system, which is quite computationally expensive. It will take a lot of computer time because here the size of the problem will become large and it will go on increasing depending on the refinement in the mesh you are doing. More number of degrees of freedom are there, the better, more realistic model you have, more time it will require. In many cases, the time required may be prohibitive. So it may be difficult to analyze the full structure with this direct time history analysis. But nevertheless, this is the most important, most accurate method which we can have for analysis of any structure. And here we get response with time at each degree of freedom, at each node corresponding to each degree of freedom we get. And here we are not having any approximation, and this is the most rigorous analysis method. So if we are not getting, it is not possible to use mode superposition method. So we should be very clear that mode superposition method is applicable only when we are getting the modes to have 90% mass participation. Otherwise, this will be erroneous. In some cases, we also use missing mass correction. So suppose I have considered sufficiently large number of modes, still I am not able to get the 90% mass participation. In that case, you look at the mode shapes of the structure and you will find that there are certain components. For example, in the vertical direction, and it will be demonstrated by Moe in the evening, that in vertical direction, it is possible to excite the superstructure. Superstructure will vibrate, but the substructure will not vibrate. And as a result, the substructure will remain more or less static, or rather it will be moving rigidly with the ground. That is more appropriate to say. So it will move rigidly with the ground. So you will not get any mass participation from the substructure. So for that, we have to make a static force calculation where the mass will be simply multiplied by the ground acceleration, and we can add that to our response spectrum or mode superposition method. So that is another alternative. But more accurate method, if we are not getting 90% mass participation, is the direct time history analysis. Now, when we are performing time history analysis, the time history analysis may be either model in different modes, or we can do the time history analysis of the structure as a whole. In both the cases, we need ground motion. So this is the most cumbersome task to achieve, to get the appropriate ground motions. In afternoon talk, I will focus on this and we will discuss more in detail. Then IRC SP 114, it has been revised very recently. In fact, it is just under revision. And SP 114 provides the guidelines in more detail for analysis of bridges for earthquake. And it provides which type of analysis is applicable in which case. In which case we can go for equivalent static method. So this equivalent, this ESAM, this is the equivalent static analysis method or elastic analysis method, we can say, or equivalent static method, we can say. So this equivalent static method, this is a single mode method. So we are considering single mode, and all the mass of the bridge is assumed to participate in that single mode. So we get the period from this mode. So period will be obtained from dynamic analysis of the bridge only, that is eigenvalue analysis or free vibration analysis. So from free vibration analysis, we will get the period. Corresponding to that period, we will read spectral acceleration from our response spectrum, design response spectrum, and then we can multiply the whole mass with that spectral acceleration, we will get the design force. So this is the equivalent static method. The other one is elastic response spectrum method. So ERSM. So this is the response spectrum method. Equivalent response spectrum method is a dynamic method. It is as good as time history analysis, provided we are able to get 90% mass participation. So if you are doing an analysis where 90% you are considering the modes having 90% mass participation, you can go for ERSM. So ERSM is most commonly used method, as you will see in this table also. Most of the places it is ERSM. And linear time history analysis, LTH. So where we are not able to get 90% mass participation, it is not possible to excite, and you have a doubt that whole of the mass of the structure is not participating, you go for linear time history analysis. In time history analysis, all the modes are inherently considered. So it is considering all the modes. So where we have a doubt regarding the total mass participation, adequate mass participation, we should go for linear time history analysis. So like that, the code suggests based on the height, based on the skewness and the curvature of the bridge, and based on the type of the bridge, which analysis method we should use, which analysis method is recommended. And this is the minimum method. So you can use a more sophisticated method, but you cannot use a less sophisticated method than what is given. And as I told you, you can see at most of the places it is ERSM. So equivalent response spectrum method or elastic response spectrum method, which is nothing but the mode superposition or response superposition of the response of the structure in different modes. That is the most commonly used method. Most of the places you will find that. Now, in case of bridges which are located on soils which are susceptible to liquefaction, because liquefied soil provides very little resistance. So there we may have to take into account the soil deformation. We cannot ignore soil deformation there. Soil deformations may be significant in other cases also, and we have to take into account the soil nonlinearity also. So in that case, we have to use either equivalent linear response spectrum method or equivalent linear time history analysis. So in this equivalent linear time history analysis, please correct this error. I'm sorry. This is EQ, not EG. EQ stands for equivalent. So equivalent linear time history analysis. So equivalent linear time history analysis, we are making a linear model. We are performing time history, but the stiffness of that linear model we select in such a way that it is representing the secant stiffness at that displacement. And because we do not know the displacement in advance, we will assume some displacement, calculate the equivalent secant stiffness, and with that we will perform a linear time history analysis and check that the displacement which we are getting from our equivalent linear time history analysis is matching with the displacement which we have assumed initially to calculate the stiffness. If not, we have to do iterations. So like that, different methods are given, but when our structure or the bridge is subjected to some devices, which may be either dampers or shock transmitting units or seismic isolation bearings, which have nonlinear behavior, then it may be difficult to represent that by a linear system. And in that case, we may have to go for nonlinear time history analysis, which is the most sophisticated, but at the same time, most computationally challenging. So it may require a lot of, not only it requires a lot of understanding of the model. So in this course, we are limiting our discussion to linear methods only. So nonlinear analysis, I'm not talking about. Nonlinear modeling requires additional properties, additional information to be defined so that the nonlinear model can be created and nonlinear analysis can be performed. Now, one very important aspect in our analysis and design of structures in general and bridges particularly is capacity. And there are a lot of confusion in the industry related to capacity design. So quickly, I will cover this capacity design also. So this capacity design is, we can understand the behavior of the capacity design. Hello, is it okay? Are you able to hear me?
Yes, sir. Yes.
Okay. So capacity design, we can understand with this analogy with the chain. So as I said that in bridge also there are number of components right from superstructure to foundation and soil. So there are bearings, abutments and piers. So only some of the components here are ductile. So in our bridge structure, the pier is ductile element Rest all elements are non-ductile. So those cannot dissipate energy until unless we are provided special devices like dampers and the base isolation devices. So those will also be ductile and those can also dissipate energy. But in normal bridges, when the special devices are not used, only the piers are the ductile components, all other are non-ductile components. So we can represent its behavior by a chain where different components are added in series. And when we are subjecting this chain to large force, more than its capacity, it is going to fail. And it is having only one ductile link, all other links are brittle. So how its failure will be? So its failure, whether it will be ductile or brittle, we can control. We can uh, make the behavior ductile just by ensuring that these brittle links, which are shown by this white color, the strength of these links is more than the strength of the ductile link. So in that case, the failure will be occurring in ductile link only, and hence the failure will be ductile. On the other hand, if the strength of the ductile link was more than any of these links, then what will happen? The ductile link is not going to fail. That link, which is the weakest, that is going to fail, and the uh, behavior of the whole chain will become brittle. So we can make the whole chain behave in a brittle manner or a ductile manner, and similarly our structure to behave in a ductile manner just by ensuring that the strength of all the brittle modes should be higher than the strength of the ductile member. So please note here, I'm not saying that the strength should be more than the earthquake. The strength will be still less than earthquake. And this is the philosophy of earthquake resistant design, that we are not designing our structures to be stronger than the earthquake. The structure is still weaker than the earthquake, but we want that the behavior should be ductile so that the structure can dissipate energy, and through that dissipation of energy, it can take care of the ductile behavior, or it can resist, our structure can resist the earthquake. So this capacity design is nothing but ensuring the capacity of all brittle links to be higher than the ductile links. So in case of buildings, this is obtained by ensuring that the columns are stronger than the beams, because beams are more ductile than the columns. The columns, because these are subjected to axial load also, so when it is subjected to axial load, their ductility reduces. So columns are less ductile, the beams are more ductile. That's why we design our buildings in such a way that the columns are stronger, the beams are weaker, and what we call as a strong column weak beam design. But in case of bridge, it is not possible. Generally, there are no beams. Even if it is a multi pier or multi-column pier, multi-column band, so we can see here also that there are no beams, and in that case the plastic hinges can form only in the piers. So if it was single pier, the plastic hinges will form at the base only. If we are having multiple piers, then some framing action will come due to the slab at the top or the superstructure, and then the hinges can form at the top also. So what we have to understand is that the piers are the ductile members. So that's why all other members, whether it is bearing, foundation, or superstructure, that has to be stronger than the piers. So first we have to fix the size and reinforcement of the piers after our analysis, and then we should ensure that all other components should be stronger than that. So in case of a single pier, the plastic hinge can form at the base. Let us say the reinforcement and size what we have provided provides us a moment capacity m naught. Then the total force, maximum force corresponding to this m naught, we can calculate just m naught by h, where h is the height. So it is acting like a cantilever. So hinges will form at the base alone, and force is just moment divided by h, or moment is just force into h. And the same force H will be transferred to the foundation, and in the foundation, if it is a pier cap or a pier group type of foundation, then from pier cap it will be transferred to different piers, and total sum of these pier forces should be greater than this H. So if it is just equal to H, then there is a possibility of formation of the plastic hinge either at the pier or at the in the piles. But we have to ensure that the total capacity of the piles should be more than what force is occurring in the pier when the pier is yielding. Similarly, if it is a multi-column band, there will be double curvature bending, and when it is bending in double curvature, the hinges will form at top and bottom, and the horizontal force we can calculate as 2 times m naught by h by 2. So because there are two columns, so that's why 2 m naught by h by 2 because it is bending in double curvature, so the effective height will become h by 2. So we can calculate h like this, and again we have to ensure that any component, whether it is bearing or foundation, it has to be designed for this force or some force larger than this, so that the hinges can form only, or the plastification or damage can occur only in the piers. The damage does not occur in the foundation. Now, to summarize this capacity design concept, the capacity to resist and dissipate energy is related with the nonlinear response of the structure. So in case of earthquake, we are always designing our structures to get dissipated. Suppose I don't want to design my structure to damage during earthquake. So in that case, I have to consider R is equal to 1. The response reduction factor will be considered 1 and our structure will remain elastic during earthquake. But if I am using R factor, value of R greater than 1, then it will undergo some damage, and that damage will lead to nonlinear response of the structure, and due to that nonlinear response, inelastic nonlinear response, the structure will dissipate energy. So the earthquake, whatever energy earthquake is imparting to the structure should be able to dissipate that energy at a larger rate than what is the rate of inflow into the structure. And if the structure is ensured for ductile behavior, so these locations to obtain this ductile behavior when we want to dissipate the energy, the location of the plastic hinges should be pre-selected. So how we can select the location of the plastic hinges? By making all other locations stronger than the location where we want the plastic hinges to occur. And why we want the plastic hinges to be pre-located? Because especially in RCC members, it is true for steel members also, we need special detailing so that we can get enough ductility. So to ensure that, we should know where during the real earthquake the yielding will occur, and so that we can provide those ductile detailing at those locations. And all other regions, all other points within all other components within the bridge or the structure should be stronger than, not earthquake, but stronger than the piers, so that those remain elastic. And within piers also, we have to avoid the shear failure, because RCC components RCC members are ductile only in flexion. As we have seen in case of columns, when the axial load comes, the ductility reduces. That's why the ductility of a bridge is much less than the ductility of a building, although both are properly designed. So that's why the response reduction factors, which are given in codes, either railway codes or highway codes, the response reduction factor in case of bridges is much less as compared to what you get in case of buildings in IS 1893. So only the shear action is ductile, the flexural action is ductile in case of RCC members, and we have to avoid shear failure. And to avoid that, we have to ensure that the shear capacity of the beam or the column or the pier should be higher than its flexural capacity. Okay, and our superstructure during earthquake should remain elastic, because there is no location where in the superstructure where we can dissipate energy, where we can provide ductile detailing, and it will be able to dissipate the energy. So we design our superstructure in such a way that no hinges are forming in the superstructure. The hinges are forming in piers only. And similarly, the bearings and connections, those are also to be designed to remain stronger than the pier. So whatever maximum capacity of the pier is there to register the force, we calculate that, and bearings and connections we design for a force slightly higher than that. So to take into account the unforeseen things and some of the foreseen things also, we considered the design capacity of these or design forces in the bearings and connections higher than the pier. And similarly, the force demand on the foundation and bearing should be based on plastic capacity of the car. So we will first provide reinforcement in the pier, and then we will calculate the provided capacity, and that provided capacity we will use for design of bearings and other. Okay, so this we have discussed. Just I wanted to discuss an interesting example. The failure here, please have a look at this failure and this failure. Both the failures occurred near the curtailment. So curtailment of reinforcement during earthquake is a very tricky issue, and that's why the code, IRS code, railway code, suggests that in case of short piers up to 30 meter, we should not have any curtailment. So pier is like a cantilever, okay? So the bending moment will go on reducing, it will become zero at the top. And to take advantage of that, in Japan, they have curtailed the longitudinal bars in the pier around the mid height. And the failure occurred only due to this. Rest everything was followed, even the tile detailing was followed. But due to this curtailment, it failed. And how? That I will explain. So let us say there is a pier and it is subjected to some force, horizontal force at the top where the mass is lumped. Then the bending moment diagram, we understand it will be linear. So it will be, bending moment will be maximum at the base and it will be zero at the top. And when we will be designing for this bending moment, the capacity we will be providing something like this. So there they have provided capacity like this. At the bottom, they have some overstrength. So because the provided capacity will be almost more, and then they have performed a curtailment here. So in the bottom portion, the capacity is this much. In the top portion of our curtailment, the capacity is this much. Now during earthquake, what can be the maximum value of this force? The maximum value of force will not be the one which we have used in our analysis. It will be rather the one corresponding to the moment capacity here. So actual moment capacity is higher than this. So the bending moment diagram will change, and the bending moment diagram will be like this. So this force is going to increase till the moment here is exceeding its capacity and it starts yielding. So you can see that in the original condition, our pier was safe everywhere, even after curtailment. Taking into account curtailment also, it is safe. But in the real bending moment diagram, which will occur during earthquake, we can see that it is unsafe here. And when it is unsafe here, it will collapse. And it will collapse in a brittle manner. Okay. So there are some other aspects also which may be important, but I'm skipping those. I will not talk about that because I have consumed my time. So I want to keep some time for your questions, so for your question answers. But we will make the PDF of these presentations available to all of you, all the participants, and you can look these slides. These are self-explanatory. You can understand that. So I think I will stop here about my talk, and now I will take up your questions. So Aman, have you compiled the questions, and can you take up those questions one by one?
Yes, sir. I have compiled the questions.
Okay, so please go ahead with the questions. You read the question, I will try to answer.
Sure, sir. Mr. Jay wants to ask, for soil, generally we are considering linear springs in seismic analysis without damping constants. To what extent will modeling the damping constants of soil be helpful in reducing seismic forces in the bridge?
Not much, because the deformations, most of the deformations, even when you are considering soil as deformable, most of the deformation is occurring in the superstructure. So even when you consider damping of the soil, it is not going to cause much effect. So that's why in many cases we ignore. So you will not get much advantage from that.
Okay. Mr. Sudeep wants to ask how to model shear key, means pounding or arrestor, means to account for the pounding action of the superstructure, how to model a stopper or arrestor.
Okay. So when we are modeling the stoppers or uh, other types of devices which are based on impact, there are two issues. One issue is the high stiffness of the shear key or this stopper, because it is small and stocky, so it is having very high stiffness. So that is one aspect. So we can model it using a gap element where we can define the gap equal to the gap between the superstructure and the stopper, and then it can be assigned a high stiffness. So one thing is its high stiffness, which we have to take into account. Another is the impact, because there will be also impact. So generally what we do, the impact modeling, which is quite complex, we ignore, and we consider this by having an element which is having almost zero stiffness till the two come in the contact, and after that the stiffness increases significantly. So this type of analysis we can use for modeling stoppers and shear links.
Okay, sir. Mr. Bharat is asking, should we take the advantage of additional displacement resulting from rotation of foundation in calculating time period?
That you are when you are considering period of the solid structure interaction, you will do that, but you won't get much effect of that on the period. So don't always think of advantage always, okay, because the displacement which you are thinking of advantageous, actually it will cause a lot of disadvantage also. So a slight rotation at the base is going to cause a lot of P delta forces. So it is not always beneficial that you will model soil structure interaction and you will get benefit. The period is going to elongate, and due to the shape of the responsive spectrum, the forces are going to reduce. Always it will not happen. In some cases, it may give rise to larger bending moments in the pier also.
Okay, sir. Mr. Suraj is asking, can you please explain the method for missing mass correction, as IS 1893-2016 can also suggest the missing mass correction, but doesn't give any method on how to do it?
Okay. So missing mass correction, what is this missing mass? Missing mass is that portion of the mass of the structure which you are not able to excite even with sufficient number of modes. Why we are not able to excite? Because its frequency is very, very large, very high frequency. And high frequency means that it is like a rigid, and I will explain in the afternoon class. When we have a very rigid structure, it is moving along with the ground. So its acceleration will be same as that of the ground. So we can simply multiply it by Z, which is the value of spectral acceleration at zero period. So very high frequency means very low period, roughly zero period. So if you have taken all the modes up to 33 hertz, and you are not able to get sufficient modal mass participation, then those modes which you are not able to excite will have frequency more than 33 hertz, or the period less than 1 by 33.03 second. So those masses, or that portion of the mass, will be moving rigidly with the soil, so with the ground. So what you can do is that mass you can simply multiply by Z, and that force you can add to the forces which you have got from the modal analysis. So that will be the additional force. That is missing mass correction.
Okay. Mr. Saravanan is asking, can we consider portal plasticing in portal beams supported by columns?
We can consider, but in case of bridges, we do not allow the hinges to form in the beam. Even if it is portal, we do not allow. And the reason for that is that when it is subjected to hinges in the beam, its vertical load carrying capacity is compromised. Because in case of building, if a beam fails, it will give rise to only local failure. But in case of a portal pier, which is subjecting the superstructure, it is subjected to very high vertical load due to dead load and live load itself, not only because of earthquake. So in non-seismic condition also, it is subjected to large forces, and we will not like the loss of the vertical load carrying capacity due to hinging of the beam. So generally there also we make is beams stronger than the columns. So we follow the reverse principle in case of bridges as compared to the buildings. In buildings we are making columns stronger than the beams. In bridges we are making beams stronger than the columns, so that the hinges are forming in columns but not in the beams.
Mr. Bush is asking, what is the hinge length and how to calculate in case of pier?
Actually, this hinge length will be required in nonlinear analysis. In linear analysis, most of the times people get confused with in what height we should provide special confining reinforcement. So the height in which we are providing special confining reinforcement is different, and the plastic hinge length which we use in nonlinear analysis is different. So please do not combine the two. Do not mix the two. The length in which the special confining reinforcement is to be provided, that is already specified by the code. So that we should do. If we are using, we want to perform nonlinear analysis and we need the plastic hinge length for the purpose of calculating the inelastic deformation in the plastic hinge, then again models are there, but that is roughly d by 2, where d is the depth of the element in that direction in which it is bending. So for example, if it is a rectangular pier, then in each direction the corresponding depth we can take as the plastic hinge length. If it is circular pier, we can take half of the diameter as the plastic hinge length.
Okay, sir. Direct time history analysis requires suitable time histories. Can you suggest how to get those?
Sure. In the afternoon, we will have a full lecture on that, because we understand that's the most complex problem which is bothering our designers. So we will have a complete talk. We have, we have planned on that, and then we will also have a hands-on demonstration where we will show how you can use the websites which we will be suggesting you to select appropriate time histories.
Mr. Pulkit is asking, is it possible to model shear plastic hinges similar to flexural plastic hinges? And what will be the input in such a case?
Shear plastic hinges can be modeled, but as I said, the shear failure itself is brittle. So there will not be any plastic deformation. So these hinges are simply elastic deformation and then sudden failure. So it's not really like a plastic hinge. Okay, but in some elements where you are able to provide some plastic ductility in plastic failure mode also, you can model in the same way as we model the flexural hinges. In case of buildings, the details are available in ASC 41. So if you are modeling a building, no such code is there for bridges where you can get the plastic hinge length, etc., and how to model shear and flexural hinges. But in case of buildings, those are available. The difference is that the sizes of the beams and columns in case of buildings is smaller. In case of bridges, the size of columns may be huge. So how much the same modeling will be applicable here, how much difference will be there, that we need to see. But some guidelines we can get from SC 41.
Okay. Mr. Lalit is asking, while doing response spectrum analysis for closely spaced mode shape, shall we do CQC for modal combination or directional combination? What is this directional combination actually used for?
Okay, so earthquake has 3 components. Earthquake rather has all the 6 components. So during earthquake, the motion at a point has all the 3 translation and all the 3 rotations. All 6 types of motions are there. Instruments which are available so far cannot measure the angular acceleration. So that's why this angular acceleration you will not find in most of the textbooks. And it is also believed, because we do not have the record so far, so we can't be sure, but it is believed that the effect of this angular rotational acceleration will be less. But translations are also there in the 3 directions. So when we are performing our analysis, generally we are considering one component of earthquake at a time. So when we have one component of earthquake at a time, then we need to combine the effect of earthquake motion in different directions. So for example, it may be in X, Y, and Z. So I can perform analysis in X separately, performance in Y separately, performance in Z separately. So CQC will be used to combine the effect of different modes in a direction. So when I perform X direction, I will consider several modes in X direction also. We will use CQC there. Similarly, I will perform the analysis in Y direction, I will use CQC. And then these two can be added SRSS. And we can see that SRSS is nothing but the factorial sum of X and Y. Alternatively, the code also says that 130 rule we can use. We can consider 100% because when the peak X load is occurring, the peak Y load or peak Z load is not occurring simultaneously. Those will be occurring at different instants of time. So we can consider X 100%, Y 30%, Z 30%, and so on.
Yes, sir. Mr. Sachin is asking, can the curtailment be carried out in case of zone 2 and 3 after checking designing for R is equal to 1? As many times the governing force is wind or accidental loads and not earthquake in case of zone 2 and 3.
So in case of R is equal to 1, we are designing our bridge not to get damaged. It will behave elastically. So theoretically, there is no need of any ductile detailing as well as check on the curtailment. Based on elastic behavior, you can do that. But we have to understand that earthquakes more than what we are considering in our analysis or design are possible. Even if we are considering MCE, maximum considered earthquake, there is 2% probability of that getting accident. And normally our design is for DV, not for MC. We intend, this is our intention, that our structure should not collapse under MC, but actually design is for DV. So we have to understand that earthquakes larger than what we are designing for, even with R is equal to 1, are possible. And in that case, the ductility capacity may be required. So that's why it is a good practice that even when we are doing R is equal to 1, we should do capacity design. We should do ductile detailing, even with R is equal to 1. Code is not clear whether it is required or not. I have participated in code committees and I have seen there is a lot of confusion in the code committee also about that. So theoretically, yes. Theoretically, you can say that I have designed my structure to remain elastic, so no need of ductility. But it is a good practice to take care of unforeseen things which will occur during earthquake.
Okay, sir. Mr. Jay is asking, to get mass participation factor of greater than 90%, we can also go for Ritz vector eigenvalue analysis rather than
we can
direct
do.
time.
So thank you for providing this information. I should have also included that. So sometimes the eigenvectors which we are getting in usual modal analysis, these eigenvectors or eigenmodes cannot provide us 90% mass participation, but Ritz vectors can provide. In that case, we can go for Ritz vectors. That is allowed.
Okay, sir. Then we have question from Mr. Jay only. What is the difference between equivalent LRSM and ERSM?
Okay, so ERSM is conducted for elastic structure. Equivalent LRSM is done for nonlinear structure, but iteratively performing a number of elastic analysis. So what we do in case of an elastic structure, when it yields, its stiffness changes, and stiffness depends on the displacement. Larger the displacement, less will be the stiffness, and this stiffness is defined using secant stiffness. So when we define secant stiffness, we can take into account the variation of the stiffness due to displacement. But we do not know how much displacement will occur prior to analysis. That we will come to know only after analysis. So what we do, we will assume some displacement, calculate the secant stiffness corresponding to that, perform a linear analysis, and if assumed displacement was correct, the answer of the linear analysis will be the same. So in case of ELRSM, we are performing one analysis. In case of equivalent LRSM, we are performing multiple analysis iteratively till we get the assumed and obtained displacement same.
Okay, sir. The question is from Kamlesh. if we design pier at base using R is equal to 3 and provide 1% reinforcement till plastic hinge location and curtail reinforcement after development length and provide the required reinforcement as per biaxial bending moment, or should we continue it to the full height?
Yeah, so what is the question? I mean, perhaps they want to know whether this is okay or not.
Right. Means should we provide the reinforcement that we are getting at the plastic hinge location to the full height, or we can just curtail it after development?
Now, that's what I explained. You can curtail it, but you should ensure that whatever capacity you have finally provided at the base, the revised bending moment diagram. Okay, so as per the revised bending moment diagram, also your curtailment should be safe. So plastic hinge should form at the base, not at the point of curtailment. You have to ensure that. And for that, what you have to do, you have to calculate the provided capacity at the base, draw the revised bending moment diagram, calculate the uh, uh, demand at the curtailment point based on this revised bending moment diagram, go LD beyond that, and there you curtail. So you have to follow capacity design principle. You can do that. And to avoid such issues in case of tall piers in case of short piers where you are not getting much advantage or saving, also the code says that let's not go involved in this in case of short piers up to 30 meters. If the pier is taller than 30 meters, then you go for all this.
Okay, sir. We'll take a couple of questions more, and then we'll take a break.
Right, because we should at least keep 5 minutes for the break,
right,
so that the next lecture can start on time.
Right. Can you please elaborate further on the torsional response of bridge with unequal pier height?
Well, elaborate more can be, it is an open-ended question. How much I should elaborate? Only thing is that we have to understand that it is like torsion in the building. So in building also, when one frame is flexible as compared to the other frame, or one side is flexible as compared to the other frame, there is torsion of the floor slab. In the same manner, in case of bridge, if a span is supported on two piers, where one pier is stiffer as compared to the other pier, the flexible pier will deform more, and due to that there will be a torsional motion about the vertical axis, and for that we need to consider the 3D model of the bridge.
Okay, sir. We'll take the last one now.
Okay.
In case of earthquake, plastic hinge will form in the pier and an energy dissipation will occur. Would this mean we have to help monitor the pier every time there is an earthquake? And what are the current practice to do the same?
Right. So this is important. That's why we do not want the plastic hinge to form in foundation. Some of the people say, I mean, pile, when I was talking about pile foundation, pile is also like a column. And we can design those piles also to develop hinges. But the problem is inspection only, that it will be very difficult to inspect the piles after the earthquake, what has happened there. So that's why we limit our plastification or plastic hinge formation or the damage to the base of the foundation, base of the pier, sorry, and that we can inspect. So after any earthquake, we should go, the practice is that the authority or the inspector will go there and they will examine thoroughly, especially the pier base, that if there is any sign of cracking or damage. So I think we can close here. We have already consumed our time. Remaining questions, when our time will permit, we will try to answer all the questions. So this is most important. Your questions are more important than the talk, but we will talk about those. We will take up all the questions in between where our time is there. Otherwise, we will write the answers. We will prepare written answer to those questions, and that will be circulated among all the participants. So now we will break for 5 minutes. Please come back exactly in 5 minutes. Very short break, and then Professor P.C. Ashwin Kumar will start his talk. Thank you.
We can schedule at 11:35, sir.
Okay, 11:35. Fine. So five minutes we are delaying. So 11:35, and then next one we will perhaps come on time. Okay. Thank you.